So if you remember last time, I didn't quite get to the end of the slides last time, so I'm just going to cover them very quickly. So last time I talked about a bunch of nice ways to handle exposure bias and other problems that we get from training models simply. There's also a couple simple methods that you can use to fix your problems without quite as much work. Hang on one second. So what's wrong with the structured hinge loss that I introduced last time? Basically, it will work in many cases, but the problem is it considers few hypotheses. So if you remember last time, just a refresher for last time, I talked about how the structured hinge loss basically generates a negative example and then penalizes that negative example. It doesn't consider all of the words in the output, or it doesn't consider all of the possible hypotheses like maximum likelihood does. This is a common problem that you'll see in any model that basically generates something and then tries to penalize it. So there's also reinforcement learning models. There's minimum risk models that Max is going to talk about later today. All of these models tend to be less stable than maximum likelihood training. So this is something that you should know before you try to apply these models. They're not trivial to get them to work, even if they do work well when they do. It also requires decoding, so it requires generating output, so it can be slower than other methods. And because of this, it's very, very common to resort to pre-training your model using maximum likelihood and then fine-tune it with these more advanced strategies. So in other words, we'll first train a model with maximum likelihood, initialize our model, then start with a more advanced strategy. There are other methods that allow us to get many of the benefits that we get from these methods without doing as much work, and also they tend to be more stable even if you start just by using these. One way to do it is sample mistakes during training, but do it on a kind of local basis. There's a method called Dagger, which was actually invented by people here. It's also known as scheduled sampling, which maybe people have heard of, but basically they're the same thing. The main difference was that Dagger was not applied to neural networks, and scheduled sampling has a slightly different strategy, for tuning the rate at which you schedule mistakes. But basically, Dagger, I think you should probably refer to it as Dagger. So the idea here is that if we have some sort of output and we have some sort of teacher forcing model, basically what we do is every time we do two different things. We calculate our scores using the same model, but when we calculate our loss function, we predict the correct answer. But then when we choose the thing that we feed back into our network to make our prediction, we sample something. So in other words, every time we might sample a wrong answer and we feed it back, we feed that wrong answer back into our network, and this makes our network more robust. It's also very common to have a schedule. So we have a schedule where we don't sample any mistakes. We just use the standard teacher forcing method. Then gradually, as our model gets better, we increase the number of mistakes that we do. That's what the schedule means in scheduled sampling, and Dagger has a similar mechanism, basically. Here, I showed an example where we're calculating the loss with respect to the correct tag. This is probably a reasonable thing to do for something like part of speech tagging. So even if you get a bad input, you still want to predict the correct tag next time. But it makes a little bit less sense for machine translation. So let's say we want to generate the dog ran. And for some reason, our machine translation system isn't very good. And it skips the and just generates dog. or maybe it generates dogs. Maybe it generates the plural. And even if it's a good system, it will do this. What this means is if it randomly samples dogs, then the next time we'll calculate the loss with respect to dog. So we'll basically be telling the model, if you get dogs, you should generate dog next. So it's saying dog's dog ran is the correct answer. So this method just kind of applied as is, so will penalize things in a kind of strange way. One way you can fix this is by creating something called a dynamic oracle, which basically tells you kind of the best thing that you could predict next time. So in the case of machine translation, it's not actually super clear, but you could say, okay, we've already generated dog, so we probably don't need dog again. So next time we should generate something like ran, because that seems to make more sense in this context. This is, as I said, this is not trivial to do in MT, but it's much easier to do in something like parsing. You can actually effectively calculate the next best action given your current action sequence. So, another thing you can do is this is even simpler, you can just drop out the inputs to your model. So what this is saying, the basic idea is don't input the previous decision that you made sometimes during training. So what this means is instead of doing this, we just drop out the input sometimes and we replace it with a zero vector. So this is called word dropout. It could also be called tag dropout if you were doing tagging. So this makes sense. It's just saying that you don't always want to rely on your previous input because your previous input might be wrong. So you can generate based on whatever other information you have. Then the last one, corrupting the training data, actually Max is going to talk about this because it has a good connection with minimum risk training, which he's also going to talk about. But were there any questions about these? Yeah. How do we know the sample? What was that?
How do you ensure that the sample is incorrect or is a mistake?
Oh, so how do we ensure the sample is incorrect or a mistake? We don't need to, actually. We can just sample from the probability distribution. And if it happens to be correct, then that's great. That means our model is a good model already. But we're assuming that our model does make mistakes. If our model never makes mistakes, then we don't need to train anymore. We're done training. So the idea is basically we want to sample according to the mistakes that the model would make. You could think about maybe wanting to encourage the model to make mistakes, like the margin-based training that we talked about before. Then you could probably smooth out the probability distribution and make it more likely to make a mistake by making the probability distribution more smooth. But I myself don't know of any methods that do that, but there might be something somewhere that tried to do that. So, anything else? Okay. If not, this time we have a guest lecture from Max, our TA, because Max has worked on the content of this lecture heavily and can give us some details. So I will turn it over to him.
Okay, hello everyone. I'm Max. In this class, I will introduce the structured prediction models with local independent assumptions. So as mentioned in last class, sequence labeling is one of the typical structure prediction tasks. And today I will also use sequence labeling as our example task to introduce the models and methods. But I have to mention that the models and methods introduced in this class are not limited to sequence labeling. It can also be applied to other structure prediction tasks. So here are two classical NLP tasks of sequence labeling. One is part of speech tagging, and the other one is the named entity recognition. And for POS tagging, we need to predict a sequence of POS tags, one tag for each word. And for NER, we need to we use the BIO tagging schema to represent the entity mentions. So here we first review some models introduced in last class for sequence labeling. So the first model is the one that treats sequence labeling as the independent classification task. So here is the pictures to show how this model works. So basically, it just predicts each tag independently. As mentioned in last class diagram, this model is actually not a structured model. It is just a multi-class classifier. The second model introduced in last class is the so-called locally normalized model. So one example is the one in this picture. We can call it history-based RNN models. The basic idea is just we just input the previous tags into the current state and use that to help to predict the current tag. Here is a short summary of these models. So independent classification models rely on a very strong independent assumption. That is, when given the input sequence X, the output Y at each position are mutually independent. We can see that this assumption is really strong independent assumption, and usually it is not true in practice. Another disadvantage is that independent classification model cannot guarantee a valid or a consistent structure output. So suppose that we are doing NER and we use the BIO tagging schema. There is an obvious constraint that the I tag cannot follow O tag. So, but this kind of independent classification model cannot model this constraint. The second class of model is the locally normalized model. I have to mention that this model does not rely on any independent assumptions, which make it a really big advantage in practice. But it requires a predefined order to factorize the joint distribution into small factors. It is not hard for sequence labeling. It is not hard to find this kind of order. We can do left to right, or we can do right to left. But for some other structure prediction tasks with more complex structures like tree or graph, it is not trivial to define this order. And moreover, optimal decoding for this kind of model is impossible in practice. And we have to use some approximating decoding methods like greedy search or beam search. And at last, this kind of models suffer from the label bias problem. So any questions so far? So before I start to introduce today's globally normalized model. Mm-hmm.
For the first independent classification model, so imagine you have a bidirectional STM to compute hidden state. So basically, at each time step, the STM is hidden state and app captures the full input. So
yeah.
in this sense, the hidden state might have some chance to capture the dependency between different targets. So
yeah.
So in this case, so there's the independent classification models in some sense can capture the dependency between the target.
Yes, if you think that the RNN or STM can encode the sentence perfectly, yes, it can capture all the information you need and to predict each tag independently. But in practice, usually it's not the case, right? So your encoder is never perfect. So
from a mathematical point of view, this is independent classification. So let's say it was genuinely ambiguous. Let's say there were 3 good options for I saw a girl, or sorry, time flies like an arrow. In that case, it cannot get a consistent, or it's not guaranteed to get a consistent answer. It might be something that looks good locally, but not globally.
But the hidden state of the LSTM can somehow like have to like internally model the dependency between the Y's in the target sequence.
So I think if you think that y is deterministic given x, then your assumption is your claim is true. But y is not deterministic given x in practice. So you can think that given an input sentence, there are multiple choices of the POS text, but one is the most popular one. The other is also possible, but
It's easier to think of machine translation as an example. So machine translation, there are genuinely multiple choices, and they're all okay. They're all good translations. And in this case, it's ridiculous to not consider your other words in the sentence. For part of speech tagging, maybe it's enough.
okay. So now we have to ask if we should turn to the globally normalized model, or if we can construct a model that does not rely on too strong independent assumptions, but also makes the optimal decoding possible. One of these solutions is the conditional random fields. Okay, let's first review the globally normalized model. Basically, globally normalized model. Where is my mouse? Here. Globally normalized model assign each output sequence a score S, which is not normalized over particular decision. Here we first define the potential functions, which is just the exponential form of the score function. And so here we discuss CRF from the perspective of graphic model. So the ugly graph on the left is the general form of globally normalized model. So basically, there is no independent assumptions between this model, implied by this graph. But for first order linear CRF, which is represented in the red graph, we can see that from the notation of graph model, the joint distribution of CRF can be written as the multiplication of the potential function at each time step over the normalizer. So I have a quick question here. So what is the independent assumption implied by CRF? So can anyone answer this question? What is the independent assumption behind CRF?
First order not-all properties.
No.
Conditional independence.
What kind of conditional independence?
Conditionalness.
No.
It only depends on the previous diagonal.
No. So if you are familiar with graphic models, the independent assumption is given, for example, given by 3, the y on the left-hand side are independent with the y on the right-hand side. So if given by 3, y1 and y2 are independent with the following parts. So, okay, so now let's see the form of the potential functions. So generally speaking, we model it with 3 parts. The transition score based on the transition feature function T, and the state score with the state feature function S and the bias. So in deep learning, we just replace the feature functions with the feature extracted from some deep neural networks. So here we can use, here the F is our feature function, which is the output of some neural networks. It should be noted that from the general form, we need to assign a separated parameter vector to each pair of the labels. So which means that we have the number of parameters is the square of the set of tags times the dimension of the feature. So in practice, sometimes this number is a little bit too large. So alternatively, we can use a simpler version, which is we just assign a single score to represent the transition score. And this method can significantly reduce the number of parameters. And this picture shows how we can combine bidirectional LSTM with a CRF. The idea is just using the hidden state at each time step of the LSTM as the feature vector of the CRF. So, any question here? Okay, so in the next section, I will show how we can train the CRF model and how to decode the output from it. So here in this slide, we first put the formulation of CRF here, and we can see that the computation of the numerator is straightforward, and the difficulty is only to compute how to efficiently compute the denominator CX, which is also called the partition function. And for decoding, we need to find the output Y that maximizes the conditional distribution. So for both of these two problems, we need to go through the entire output space of Y, which grows exponentially with the length of the input sequence. But fortunately, for CRF, we have the efficient algorithms to solve them. Before I introduce the well-known Viterbi algorithm, I want to first do some analysis to get some insight of this algorithm. So here, let's see the computation of the partition function CX. We can see that each label depends on the input, or each potential function depends on the input and the nearby labels. And given the adjacent labels, others doesn't matter. So if we knew the score of every sequence from Y1 to Yn-1, we could compute easily the score of the sequence from Y1 to Yn. So we really only need to know the score of all the sequence ending in each Yn-1. We can think of that as some pre-calculation that happens before we think about Yn. So based on this analysis, we can introduce the Viterbi algorithm. So we first define the pi t y given x as the partition of sequence with length equal to t and with label y. So the pi, okay, so pi t can be expressed as the summation over all the sequence of length t minus 1 and times the potential function at time t. Because the potential function at time t only depends on the previous label, so we can put it outside the summation. So we can put the potential function at time t here, and this part is just pi t minus 1. Then we get the dynamic programming algorithm. So finally, to compute Cx, we just need to sum over all the sequence of length L, ending with all possible y. So the algorithm is really simple. So we can use a concrete example to interpret the Viterbi algorithm. Suppose that here it's not Cx, it's log Cx. So here the algorithm calculates its log CX. So a quick question here is like, why we want to calculate log CX, not CX? In practice, we usually directly compute log CX. We do not compute CX. Does someone know why we do this?
You can just add the probabilities together. You don't have to.
It's not the real reason.
A floating point explosion.
Yes, that's the point. Yeah, because in practice, CX is sometimes it's pretty large and it can incur some numerical issues like big number of flow. So we need to compute CX, log CX, instead of compute CX. So this example is to show how could we compute log CX. So at first step, we compute the score of the first word with all possible POS labels. So the score here is the transition score plus the state score. And in the middle of the dynamic programming algorithm, we need to enumerate all possible POS tags that previous sequence ending with, and then the score of the current state is the summation of the score of previous state plus the score of the current time step. Here, the log sum ext function is defined here. It is we first take the exponential of x and y and plus them together and take the log.
So one comment about log sum x. When you actually do this in practice, this is what you want to do.
Yeah.
But you also actually take the maximum and we set this equal to m. And then before So when we take the log sum of x, what we actually do is we subtract this, this maximum here. And the reason why is for numerical stability problems. Because if you actually took the exponent of x as is, you'll end up getting either infinity or 0. So don't implement your thing exactly as Max put it up there, because you'll have the exact numerical stability problems we talked about. You actually do need to add this, this maximum taking step. Or if you expect your number to be very large, you might need to take the minimum instead. Or is the maximum always okay? No, you might need to take the minimum if you expect the number to be very large. So yeah, I just thought I would add this just because some people in this class might try to implement this as is, and they'll run into trouble. So this is important.
Okay. So as the final step, we just collect all the scores to compute the partition function. So, okay. The previous algorithm is just to show how could we compute the partition function. And for decoding, we can use the similar dynamic programming algorithms for the decoding. And in practice, in order to train CRF, we need to calculate the gradient with respect to the loss function. For loss function, if we use MLE training, then the loss function is just a negative log likelihood. So let me see. Okay, so I put the expression of the gradient here. So we see that in order to compute the gradient, we need to compute the expectation of our feature vector with respect to our model distribution. So the algorithm to solve this one is called forward-backward algorithm. the basic idea behind this algorithm is like both the distribution and the feature vector can be composed into small factors. And we only need to compute the marginal distribution like this. So if you are interested in the details of this algorithm, you can read the reference paper. But for deep learning, we are very lucky because we do not need to do the gradient by ourselves. The deep learning framework can automatically do the gradient for us, so we do not need to worry about this. And the only thing we need to do is to compute the loss function. So any question here before I start next? Okay.
How did the deep neural network framework to calculate the gradients? Is this using the forward backward or it's?
Yes, actually. So if you still remember the first class when Graham described the computational graph, then it is straightforward. So we just define the gradient of each operation and just combine the gradient using the chain rule. So actually, they do the same. They do the forward backward algorithm for yourself for you. So
Yeah,
algorithm is the same.
you can think of it as you have to implement the forward step, but then the DNN framework automatically does the backward step for you when it does back propagation.
Okay, now let's see how well the CRF model works in practice with a case study. So actually, it's one of our papers published in last year's ACL. Okay, the motivation of this work is to build a truly end-to-end neural models for sequence labeling, requiring no feature engineering or data preprocessing. So this model is able to use two levels of representations. So for character level information, we use CNN, and for word level, we use bidirectional LSTM. So this picture shows how the CNN works. So we use CNN to extract morphological information such as prefix or suffix of a given word. So here, for example, we expect that CNN can capture the information of the suffix like ing here. And we use bidirectional LSTM to model the word level information. So we concatenate the character vector and the word embedding together and use them as the input to the bidirectional LSTM. And on the top of bidirectional LSTM, we have a CRF model to model the correlation between the labels. So here is the training details. For optimization, we just use SGD with momentum, and the learning rate decays with the rate 0.5 after each epoch. And we also applied the dropout training. For parameter initialization, we use the method proposed in Grot and Banjo in 2010. And for word embedding, we use the Stanford Grove pre-trained embeddings. For character, we uniformly sample the initialization embedding around a 0 or within an interval around 0. We ran 2 experiments to evaluate our model, so POS tagging and NER. We see that both CNN and CRF can achieve significant improves over previous models. And interestingly, that CRF helps much more on NER than on POS. I guess the reason is like the label correlation in NER is maybe stronger than that in POS, because for NER we use the BIO tagging schema. There is an obvious constraint between them. So Okay.
So if we delete like the bidirectional LSTM and the CRF, delete the convolutions on the character levels. So have you ever tested?
You mean delete the convolutional? Yeah, that's
without the character level. Just
that's just the BSTM.
Oh, that one with the
Yeah.
CRF. So without.
Oh, you mean only
Bidirectional
LSTM but with CRF?
Yeah.
I did not do that experiment. Okay, so in next section, I will introduce some methods that consider rewards during training. So at first, we need to figure out what is reward functions in structure prediction. Basically, unlike the classical classification tasks, which commonly use accuracy to evaluate their model performance, in structure prediction, we sometimes have the task-specific evaluation metrics, what we call the rewards. So, for example, we use token level accuracy for POS tagging, and we use F1 score for NER. We use label attachment score for dependency parsing, and we use corpus level blue score for machine translation. So now the question is, do different reward functions impact our decisions? So to make the question more clear, here we have a simple example. So suppose that we have two tasks. The data of the data are the same. So the data are all sampled from the same distribution, P. And the task is the same. What we need to do is to predict Y given X. That means we need to deliver a prediction function H that maps X to Y. The only difference here is the reward functions. So here, for task 1, we evaluate our performance using R1, and for 2, we're using the reward function R2. So if we think about the POS tagging, then R1 can be the token level accuracy, and R2 can be sentence level accuracy. So now the question is, if the two tasks should have the same prediction function or not. So anyone who thinks that H1 should equal to H2? And who think it should be different? Okay, so the answer is they should be different. And to better understand this, we can have a very simple examples to better understand this. So suppose that we have two boxes, and one of them has money in it, and our task is to predict which box has money. So if we make the correct decision, then we get 1 million. Otherwise, we get 0. And our predictor says that the probability that the money is in the left box is 0.8. Then and our reward is the amount of money we want to get. Then in this case, our choice is obvious. We have to choose the left one because we have the higher probability. But now the setting is a little bit different. So if the money is in the left box and we pick it, then we get 1 million. If the money is in the right one, it is 1 billion. And the predictor still give us the same probability. That is 0.8 for the left one and 0.2 for the right one. So in this case, which one we should choose? So in this case, actually we should choose the right one. So that's why the reward function can change our decision. And if you are interested in this problem, you can read some materials about Bayesian decision theory, and you can get a whole picture of this topic. So, any questions about so far? Okay. So, based on the previous analysis, we know that in order to achieve better performance with respect to the reward function, it is reasonable to consider rewards during training. Here we list three popular methods. The first one is the max margin method, which is first proposed by Bentaska in 2004. So this method is similar to the cost augmented hinge loss, which has been introduced by Graham in last class. So this class I will not go into details of this method, but I have to mention that this method does not rely on a probabilistic model, and only decoding algorithm is required. So this property makes sometimes this property makes this method more flexible to be applied to different models. And today I will introduce the following two methods: the minimal risk training and the reward augmented maximal likelihood. So the loss of MRT is given here. It is the expectation of the negative reward with respect to the model distribution. Here, the negative reward is also called risk, so that's why this method is called minimal risk training. If you are familiar with reinforcement learning, you can find that actually the loss of MRT is the same with the loss we use in reinforcement learning. So the difference here is like for MRT, they directly optimize the loss function instead of using reinforcement techniques like policy gradient. So there are several advantages for MRT. First, it can do direct optimization with respect to the evaluation metrics, and it is similar to the globally normalized models proposed by Andor in 2016, and it can also consider the task-specific reward. And I think the most important advantage is like this method can be applied to arbitrary risk functions, no matter R is differentiable or not. Even though you want to do end-to-end training, R is not necessarily differentiable. So this property is really good in practice. But there are also some bad parts, and the most important one is like the computation of the expectation is intractable. So to solve this, we have to do some sampling within a subspace. And the last one I want to introduce is the reward augmented maximal likelihood. The basic idea behind RAMO is to randomly sample some incorrect training data from the payoff distribution queue and combine them together and feed them into the MLE training process. So for the queue distribution, we can see that it assigns higher probability to the output Y with better reward. So here is a picture to briefly describe how this model works. So this is the input sentence, and this one is the correct gold standard output. And based on this distribution, we sample another incorrect output and put them together for MLE training. From the theoretical part, it can be shown that RAMO is actually to approximately maximize the reward. So if you are interested in the theoretical insight of RAMO, you can read these two papers. Okay, so this is the code example, but actually has not been ready yet because this code is not written by me. So, but I still want to appreciate Chunting Zhou for sharing her CF code. I will make this code ready as soon as possible. Sorry. Okay, any questions?
Hi. Can you go back to slides?
Which one?
One. So, how is the loss optimized? It's not differentiated.
Sorry?
How is the learning done in this case? The R is not differentiable, so how do we learn in this case?
If you take the gradient of this loss, you find that because R is not the part of this model, so if you take the gradient of this loss, then you do not need to take the gradient of R with respect to the parameter.
So I can describe the procedure a little bit more also, which might make it a little bit more clear, which is basically what you do is you sample you take your X and then you sample maybe 5 different answers or something like this. Which means you have this space of samples, and let's call this space of samples S. Then your risk here, it's written as an expectation, but you can approximate the expectation or you can approximate the denominator of this by taking probability of y hat I given x. Sorry. And this is basically your reward, and then you divide by this. And your loss function is maybe the negative reward. And this is not differentiable. This can be anything. It can be like blue score. It can be F measure or something like this. But these parts contribute to the loss function also, and these are parameterized. These are differentiable. So based on that, you have a loss function where your loss function basically affects, the parameters affect the loss function, and you can backpropagate through that. So yeah.
Could you elaborate more on the difference between reinforcement learning and policy gradient and reinforcement? Like, they have the same objective?
Yeah, I think basically the objective is the same. I actually was thinking about this myself as I was listening to this, and but I think the biggest difference here is that we are not. We could basically use this with a globally normalized model as well, right? This minimum risk training, so we don't have to make. We're not conditioning on individual decisions that we make, whereas a policy gradient model has to basically condition on individual decisions each time it makes an action. I'm not certain about that, and I will talk about that 2 classes from now after I have a chance to take a look. The biggest difference practically is this one you definitely have to take multiple samples. In many policy gradient methods like reinforce, if you're familiar with that, you do not have to take multiple samples. You can just take a single sample. So there are also very practical differences, but in terms of the objective, I think they might be very similar.
Isn't this task specific reward just a constant? So how will it affect the loss function?
You can answer my jump in.
What's your question?
Isn't the task specific reward just a constant? So how is it going to affect the actual optimization?
If it's constant, what do you mean by constant?
So the R would be constant, right? Like it's
So, so for the reward function, you have a target y, right? And the small y is target y. That's the y that you use as a ground truth. And for given for prediction, then you just compare the gold standard and your prediction and calculate the maybe some difference or similarity to get the reward. So I don't know how it can be constant.
So when you do like max margin training, you have like a max.
So this is actually, I think, the same question. It's a different way of saying the same question as before, which is that this is constant, right? The R is constant, but the other parts of the loss term are not constant in the parameters. So because of that, the other parts of the loss function are the things that are resulting in back into the parameters.
Is this kind of weighted objective function? Because weighted by the additional R for some like the data that you are working very badly on, you have to add more penalty. Like that's why how the R works here, how the R. Otherwise, it looks quite similar to the normal objective function. That's my concern.
Do you have any
So
comment?
I don't understand your point. So what do you mean by it looks like normal loss?
So what is the difference between this and MLE,
Yeah.
maybe?
You mean this one and MLE?
Yes, yeah, like this one. It's just multiple addition.
So
Yes.
So there's a very close connection between this and MLE, and actually MLE is minimum risk training when you're using the 0-1 loss.
Yeah, 0-1, yeah.
So when this is 1 whenever you get the correct answer, and 0 whenever you get the
Yes.
incorrect answer, this is the same as maximum likelihood. So the only difference is that you get partial reward when you
Yes,
don't get
yes,
it correct.
Yes, that's what I mean.
Yeah.
Is it same as cost augmented theory?
you mean this one? Actually not. So for the cost augmented CRF, that is so that is you add the loss here. So this is your score function of y given x, and you add some your reward here, like let me see, I cannot remember exactly, but the cost here, right? Something like this. So that means you put your loss here, that's y star, and to redefine the score function. So there are some papers to analyze the relations between the cost augmented CRF with the standard CRF, but I don't think this one is equal to this one, or I don't think this one is similar to MLT.
Anything else?
Yeah.
So what is the relationship between the problem of choosing which reward evaluation method to optimize on and the minimum risk training?
Sorry, can you speak louder? I cannot hear you. Speak louder, I cannot hear you.
So what is, like this is a different problem. The question is which evaluation method what is the relationship between this problem and the minimum risk? Because that is
You mean this problem? You mean what is the difference between this problem and minimum risk training
or the connection.
connection?
So we had another, I think you're referring to this slide? Or kind of, or? So what is the relationship between which metric we choose? So the question is, what is the relationship between which metric we choose and like why did we talk about them in the same section? I think the reason why we talked about them in the same section basically is because minimum risk training is a way to consider this while we're creating our models. So if we're just using maximum likelihood estimation, we're completely ignoring the fact that we're evaluating on a different metric. So we might get very good likelihood, but we might get bad on that other metric because there's an interaction between our model and the metric that we're not considering during our training. So a very obvious mistake, or a very obvious thing is, let's say we have a metric that really likes sentences that are the correct length. Like Blue Score really likes sentences that are the correct length in machine translation. Maximum likelihood, on the other hand, likes shorter sentences because shorter sentences have fewer multiplications in them. So there's this disconnect, and it's important to consider what we're actually going to be evaluated on when we do optimization, which is why we introduced those in the same section, I guess. You'll notice that we only picked one metric for each of these tasks. In reality, there's other metrics, like you could come up with 10 metrics to, actually you could probably come up with 100 or 200 metrics to evaluate machine translation, and people have. You can also come up with multiple metrics for named entity recognition or whatever. If you choose different metrics, you will get a different policy, or you'll get a different model if you train using minimum risk training. But you'll still get the same model if you train using maximum likelihood. So, does that answer the question?
Yeah, actually, I wonder, how do we implement this algorithm, like the minimum risk? Just by changing the objective function? Does that work?
You mean here?
Uh-huh.
If you want to implement it this way, I think you should go into the details of the paper. So actually, what it does is, because the computation of the loss function is impossible. So what they did is, at each training step, they do sampling based on the current model, and use this sampling to approximate their expectation, and then do their update.
Yeah, so sample,
Yeah.
then calculate that loss function,
Yeah.
and then optimize that loss function. One thing I should mention is this, like most of the other structured prediction methods, is actually very hard to train properly. But I know how, so ask me.
Okay, good.
I've gotten this to work before, and there are some tricks. I can mention all the tricks now, which is they have a scaling parameter for the probabilities in their paper. That scaling parameter is very important. The number of samples you use is important. Whether you include the correct answer in your sample set is important. And also, what trainer you use is important. If you just use Atom with the default parameters, it will often not work. So if you need to lower the learning rate or other things. So there's a bunch of tricks. If you want to know all of these tricks, come to office hours and I will tell you all these tricks in more detail.
Is there also any connection between how the sampling is carried out? Like if one tries to sample in order to have greater amount of vocabulary that would ensure that the expectation is estimated properly, as opposed to sampling sentences with the same vocabulary?
I don't know with respect to this particular method, but in reinforcement learning, for example, I'm going to talk about this. encouraging exploration is very important. So what you mentioned is a way to encourage exploring different parts of the space. I guess that would probably also help here, but I haven't tried that myself, so it might be worth trying.
Okay, so one thing I need to mention is like, so for one advantage of REMO against MRT is like, so for REMO you only need to sample from a fixed distribution. This small Q distribution is fixed, so it does not depend on your model. So it makes the sampling much easier. So if you use MRT, you have to, for current model, you have to sample from this model, and you compute the current loss and do the updation. Then when you update the parameters, the model distribution has changed, and you have to sample from a different distribution. So this process makes the training somewhat unstable. So sometimes you have to use some pre-training method to initialize the model, which makes this training a little bit harder. So
one thing I should mention is that RAML is a very good choice. I think it's extremely easy to implement. In that you basically, it's a fixed distribution, so it doesn't change. You don't even look at your model. You just randomly sample the number of errors, and according to a numerically computable distribution, and then corrupt your true answers. So this seems to work quite well according to Max and others' experiments. You can take a look at this paper if you're interested. There was a mistake in the paper. Has it been fixed? Do you know?
you mean the original paper?
Yeah.
Which
About the
mistake?
sampling distribution.
Really,
Oh,
I
you didn't
don't
know that.
maybe I
Was the mistaken equation in the paper fixed?
Like the original?
Yeah.
Yes, you have like, you have link fixed.
Oh, so they updated the paper.
Probably not on like.
Not on archive. Okay. Okay. Well, if you're implementing this, apparently there's a mistake in one of the equations that's kind of important. So feel free to ask me. By proxy, I'll forward you to the correct people for details if you want them. Any other questions?
In a paper you mentioned the REML function can be shown as a KL divergence.
Mhm.
How does that work?
So actually, if you're familiar with MLE can also be written as KL divergence of the entire distribution with your model distribution. So REMO can be written as the KL divergence between the Q distribution, that is that one, between your model distribution. So that's the relation between REMO and MLE. So that's why sometimes people think that REMO is somewhat ad hoc, because when you want to minimize this kind of KL divergence, because this Q small Q distribution is not a real distribution, it's designed by yourself, right? So why this makes sense? So if you want to know why this makes sense, you can read my paper, and I will give some theoretical interpretation of why this does not make sense.
This looks a lot like variation influence.
Sorry?
This looks a lot like variation influence in the dimension, the K minimization between the simplified distribution Q and the not on this slide, on what you wrote.
You mean
Yeah.
a lot of what?
It looks a lot like variation influence.
Variable influence? I'm not sure, but maybe you're right.
But the variation of inference of the Q is not fixed. The distribution of Q is not fixed.
Yeah.
Yeah, Q is fixed.
I think the only thing that's similar is the fact that they're using the KL divergence. I don't think there's anything else similar between them, although I might be wrong. Yeah.
Can you optimize multiple objectives to
Can you optimize multiple objectives? The answer is yes, you can. And you can add together multiple objectives. And just the sum of your loss functions becomes your next objective. There's more complicated ways you can do it, but that one will work most of the time. You sum them together and then you weight one of your two objectives.
I think if you optimize multiple rewards, that means you define a new reward. Right? It's equivalent to define a new reward. That the reward is just the sum of the multiple rewards.
There's also more complicated things where you can try to, where you have basically a couple rewards that are kind of mutually exclusive, and you don't say which reward is more important. You just say you want both of them to be good, and you can define something called the Pareto frontier, which is basically like which if it's not worse than any of the others, then you can optimize towards that. I think this is interesting, so if anybody's interested, I'll be happy to give the reference for this. It's optimizing machine translation with multiple objectives or something like that is one I know in NLP. There's also lots of other multi-objective optimization literature, but I think in reality what people do almost all of the time is they create a new weighted reward where it's like a new reward function where basically you add them together and weight one of them with a constant to adjust how important it is. So. Yeah.
So in the case of MT, if you are using minimum risk training, so blue is like the corpus level.
Yeah, that's a question. So currently, all the reward function defines between one output and one target, right? So it cannot handle the case like the reward is calculated based on a corpus. So for that case, maybe we need some more complex, more powerful models. But for current models, we only care about the rewards only depends on a pair of flags. So it cannot handle your case.
So I have a good summary of this. I wrote a survey paper called Optimization for Statistical Machine Translation, a survey. And it has an entire section on how you approximate the corpus level reward with sentence level measures. Basically, the ways you can do it are either by smoothing your sentence level reward to make sure that it's not zero in the case of blue score, or you can keep a rolling average of basically the rewards that you've gotten up until now, like this, or the statistics you've gotten up until now, and do that. In reality, I don't think anybody's tried the latter one. Almost everybody just optimizes a sentence level reward and pretends like they're optimizing the corpus level reward, and then they don't discuss it anywhere in their paper. So, in neural network land anyway. In statistical machine translation land, people cared about that a lot more. There are ways to do this. Okay. So thanks a lot, everybody. I thank you for all the questions, because we finished a little early. Yes?
So when we end class, could you pick up your quizzes? Because we do have one without a name on it. So it'd be nice to know whose that is.
Yeah.
Thanks.
Okay, thanks.